Thanks for coming. Thanks for sacrificing some of your time to perhaps willingly listen to me talk about math. That's a first for me. Most people don't willingly listen to me talk about math. My wife tries, but she doesn't last an hour, I can tell you that much. I have to apologize for my title. It's a bit outdated. It's the second most beautiful theorem in mathematics in 1988, which was, 30 years ago, but it was a good hook. And so I thought maybe it'd, boost attendance. So in 1988, there's a journal, The Mathematical Intelligencer, and it sent asked its readers to rank some of the most well-known theories in terms of beauty. And number one was actually due to Euler as well. It's e to the I pi plus 1 equals 0. I'm sure that's no surprise to some of you. But number two was Euler's formula for Polyhedra, which is v plus f minus e is equal to 2. Sometimes this is called Euler's characteristic. This is the number of vertices, the number of faces, and the number of edges of the polyhedron. So here are some examples up here. This is an icosahedron. This is a dodecahedron, and then I have the Platonic solids as well. Well, this is a Platonic solid as well, but the others here. And all of them satisfy this equation. People like polyhedra. Perhaps inexplicably. I mean, some of you are probably wearing some polyhedra on you right now. They're sort of beautiful, right? We spend a lot of money on them. We adorn our bodies with them. Our cityscapes are filled with them. And we even hide money inside of polyhedra in video games. So they're pretty important to us. So I'm going to start with a little bit of history here. And perhaps what's the most amazing thing about this formula, v plus f minus e equals 2, is that the history of mathematics goes back thousands of years. And it wasn't until the 1700s that this formula was sort of uncovered. So we can really start with the Pythagoreans. This is 500 BC. And Pythagoras was a philosopher and a mathematician. He had disciples, really. He had a whole cult of people that studied mathematics. And they really were sort of a cult. They were a strange group of people that took their math very seriously. And he was very interested in geometry. The solids fascinated him, but he and his students didn't find it, perhaps interestingly. Plato, one of the greatest thinkers of all time, this is 100 years after Pythagoras. We owe his name, we give his name to the Platonic solids, so clearly he studied them, spent some time with them. He tried to apply atomic theory to them. Perhaps you heard of Plato's earth, fire, wind, and water, I think? No, not wind. What is it? Well, he tried to apply these solids to atomic theory to them. He was wrong, but he tried. He didn't find it. 50 years later, we have Aristotle. He was a student of Plato's. He also worked with Plato's atomic theory, and he added a fifth polyhedron to atomic theory and called it ether. So he clearly spent some time with the regular polyhedra. He didn't find it. About the same time, we have a perhaps lesser well-known thinker, Itis. He has his own crater on the moon. So that's kind of neat. He's actually responsible for the proof that there are only 5 Platonic solids. And that one was also on the list of the top 10. I don't remember where it fell, but he's crucial to the story. He spent some time with the solids. Clearly, he proved that there were only 5 of them. He didn't find it. 50 years later, we have Euclid, which is perhaps the most well-known geometer, though he's not responsible for much of his own mathematics. The only thing that I can think of that I use that I don't even think is due to Euclid is the Euclidean algorithm. And I don't know, maybe some of you know, is the Euclidean algorithm really due to Euclid? The Euclidean algorithm tests whether or not 2 numbers are relatively prime, or it finds the greatest common factor. Is that due to Euclid? I don't even know. It is. OK, so that's perhaps the most well-known thing that we can attribute to Euclid. But he's most famous for his textbook, the Elements. And the Elements is a huge book, geometry textbook, has a whole section that's devoted to the regular polyhedra. And this formula v plus f minus e equals 2 is missing. Euclid didn't find it. So we fast forward 2,000 years. 2,000 years of history, 2,000 years of mathematics, 2,000 years of great minds, 2,000 years of mathematical study, of new proofs, of new branches of mathematics, and still v plus f minus e equals 2 is hidden from man. So 1600 AD, we have Kepler. And Kepler is fascinated with the regular polyhedra, so much so that he proposes that the planets orbit on these globes that are contained between the regular polyhedra. So here's a picture of that. He thinks that the planets are on these circles between, these sort of shells between the regular polyhedra. His fascination with the regular polyhedra, though, ends with this failed idea. He didn't find it. Descartes. He's maybe the most interesting one in this history lesson because some people argued that maybe he did know it. He's the father of analytic geometry. He studied polyhedra extensively, and he actually did find something that perhaps resembles the Euler's formula for polyhedra. So what he found is, let me draw a cube. He found a relationship between the number of faces, the number of vertices, and the number of plane angles on polyhedron. So a cube has how many faces? 6, right? And it has how many vertices? Well, it's got 4 on top, 4 on bottom, that's 8. And the number of plane angles is something that we don't really talk about much. But the number of plane angles, each face of a cube has 4 plane angles. They're all right angles. So if each face has 4 plane angles, we can just take 4 times the number of faces, we get 24. So there's 24 plane angles on a cube. And we can see that this cube satisfies Descartes' formula here, that 24 is equal to 2 times 6 plus 2 times 8 minus 4. Does that work? 12 plus 16 minus 4? 28 minus 4 is 24. Yeah, it works. So some argue that he was so close that he must have known it. And in fact, some textbooks even call Euler's formula the Euler-Descartes formula. But I think that that's probably not true. Descartes probably didn't know it. And the reason why Descartes probably didn't know it is for the same reason that Pythagoras and the Pythagoreans didn't know it, and Plato didn't know it, and Aristotle didn't know it, and Itis didn't know it. And that's because until Euler, we as a studying mathematics, we viewed polyhedron fundamentally differently. So it wasn't until Euler that we actually looked at a polyhedron as a grouping of 0, 1, and 2-dimensional objects. So Descartes was close. Did he find it? We don't really know. Maybe he knew. But I think not. I think not. So 1707, Euler's born, most prolific mathematician of all time. Well, arguably. He was a true generalist. He published in geometry, in calculus, in probability theory, in algebra. He published his entire life uninterrupted by anything, really. He had 13 children. That didn't interrupt his mathematical output. He went blind late in life. That did not hinder his mathematical output. Truly just a gifted mathematician. And Euler looked at a polyhedron fundamentally differently than his predecessors. And it wasn't until 1750 that the term edge was really defined. This was the first time that we find the word edge. And so this is the first place we see it is in a letter to Goldbach, Christian Goldbach, famous Goldbach's conjecture. Do you know it? Any even bigger than 2 can be written as the sum of 2 primes. Still unproven. So he writes this in a letter to Goldbach. The junctures where 2 faces come together along their sides, which for a lack of an accepted term, I call edges. And so I think that this part right here is telling a lack of an accepted term. If it's not there, if it's not how we view it, then how can Pythagoras or Plato or Aristotle come up with the relationship? If it's not even an object to us, right? He probably found it by looking at a chart much like this, where you can see that the number of faces plus the number of vertices minus the number of edges is equal to 2. He didn't prove it right away. He just saw it and made the conjecture that v plus f minus c is equal to 2. He didn't miss it. So once Euler decided to think of a polyhedron as a collection of 0, 1, and 2-dimensional objects, then the relationship becomes clear. He probably found it in 1750 rather. It wasn't published until 1758, and even then it wasn't proven. It was just a conjecture at that point. And he was very clear about that from the output. He said, look at this relationship. I don't have a proof for it, but this is what I think. 1 year later, he proved it. It wouldn't be a proof by today's standards. It lacks a bit of mathematical rigor. It's a bit visually intensive. We have to do a lot of imagining to think of Euler's proof of it. And in fact, Euler's proof isn't really the one that's most commonly used in textbooks. It's quite lengthy and not very well known amongst mathematicians because there are better ones. Here's some of Euler's original work. So this is the way he had it written. I can't read Latin. I think that's Latin. So I'm not sure exactly what that says, except for the 2, which is probably the most important part. OK, so the first proof that I'll show you of this theorem, v plus f minus e equals 2, is due to Legendre. And I really, really like Legendre's proof. I'd like to show you 2 proofs. I have 3. The one that I have after this one uses induction. I don't know how many of us know about induction. So I might skip over a few slides in a minute after we go through Legendre's proof. But Legendre published a geometry textbook. And this was one that did include Euler's formula. He wrote a proof of his own. And his proof relies on the area of spherical polygons. And I really like spherical geometry. So this proof makes me happy. Excuse me while I take a drink of water. OK, so we have to have some tools in our tool belt before we can actually really understand Legendre's proof. So in general, on any surface, the shortest distance between 2 points is called the geodesic. On a plane, it's a line, right? But on a sphere, we have to decide what a line on a sphere really is. So we're going to do a little bit of a thought experiment. We're going to take a sphere. We're going to dip it into a can of paint. Did you all dip your sphere into your can of paint? OK. We're going to take our sphere and we're going to roll it along a plane so that on the plane is a line. And then we're going to pick up our sphere and we're going to see what's missing from our sphere. Okay? So that will be a spherical line. And a spherical line, you can't think about what's missing where your fingers touch the sphere. Just the part that's on the plane. So a spherical line, or geodesic, will be a great circle. It's the biggest possible circle on the sphere. Okay. So for example, or that. So I'll make the claim that this is not. So why not? What if I dipped my sphere into my can of paint and then I rolled it along a plane so that that's what was missing? What would that be? That'd be a circle. So this is a spherical circle, or you can think about that like a latitude. And these are spherical lines, or meridians or longitudes would be spherical lines. Okay? So once we have that, then we can actually define a two-sided polygon on a sphere. That can't happen on a plane, but on a sphere that can happen. Where we have two lines that intersect at 2 points. And you can see it here. And it's called a loon. We need to know about the area of a loon if we're going to be able to find the area of any spherical polygon. Right, so let's find the area of a loon. I'll use this picture here. If I call this angle A, then I'll just call this loon here that sort of wraps around, I'll call that loon A. And we can find its area really quite quickly because the angle A divided by the entire angle there in radians, which is pi, must be equal to the area of loon A. Well, my notation is, so area of the loon divided by the area of the entire hemisphere. And the area of a sphere, and if we keep it simple, we'll make the radius 1. So area of a sphere, radius 1, is 4 pi. So the area of the hemisphere then will be half that, 2 pi. OK, so the area of the loon is quite easy to find now. Area of the loon is twice the angle, twice alpha. Is that OK? I find that super interesting, that the area of an object on the sphere relies on the measure of the angle. So the area of the loon is twice alpha. This is going to help us, twice A. So the area of a triangle now we can find. So let's think about this triangle on a sphere with angles alpha, beta, gamma that correspond to points A, B, C. OK. The area of the entire surface is 4 pi if we say that the radius is 1. So 4 pi is the entire surface area. This has to be, there are 2 of these loons of angle alpha. The vertical angle theorem still holds on a sphere. if you can trust that, then you'll see that there are two loons there with angle alpha. Is that okay? Yeah. Okay, so there's two loons of angle alpha. Maybe I'll say L sub alpha. I'm changing my notation, forgive me. And there's also two loons of angle beta, and there's also two loons of angle gamma. So we have a problem, though, because I've counted the area of this triangle in the front 3 times. I should only count that area once, though. And there's also a congruent triangle on the back, and I've counted that one 3 times as well. And I should only count it twice. Or I should only count it once, so I've counted it twice too many. So I've counted the triangle in the front twice too many. I've counted the triangle in the back twice too many, and those are congruent. So I should subtract 4 areas of those triangles. So I should subtract 4 times the area of the triangle. Now we know how to find the area of loon alpha, the area of loon beta, the area of loon gamma. It's twice the angle measure. So we have 4 pi equals to 2 times 2 alpha plus 2 times 2 beta plus 2 times 2 gamma minus 4 of the triangles. Can I answer any questions at this point?
I'm still not sure why you're subtracting 4.
Okay.
I think I see 3 of them.
Okay, so what I've done is this loon alpha actually grabs the area of the triangle, right? Mm-hmm. But also loon beta grabs the area of that triangle too. Okay. And loon gamma also grabs the area of that. Yeah. So I had to subtract 2 of them from the front. Okay. That same thing happens on the back.
Okay, I'm good now.
If there is a back to a sphere?
Yeah.
But yeah. That's okay?
Yeah.
Oh, beautiful. Okay. So then we have, if we solve this for the area of the triangle, then we find that the area of the triangle is alpha plus beta plus gamma minus pi. That will be the area of the spherical triangle. Divide both sides by 4. Get the area of the triangle by itself. So the nice thing about this formula is that it generalizes much in the same way that the area formula for a triangle on a plane generalizes. So if you want to find the area of an n-gon on a plane, all you have to do is draw some diagonals from a specified vertex, from one vertex, and then you can count the number of triangles that you have, and then you multiply that by 180. If you remember your high school geometry class, then perhaps you remember that proof. Same thing works for a sphere, so this generalizes. If we have an n-gon on a sphere, then the area of that n-gon, well, we add up all the angle measures, and we subtract n times pi plus 2 pi. That is because we add up, so the area in general is you add up all the angle measures, and then you subtract pi times the number of triangles that you can make, which is n minus 2. Distribute the negative pi, and we come up with this formula here at the second bullet point that gives us the area of any spherical polygon. We can think about this visually this way. Add up all these numbers. So add up all the angles, A1, A2, A3, A4, A5. And then at each edge, subtract pi. That's from this term, subtract pi n. So at each edge, subtract a pi. And then right in the middle of your face, add a 2 pi. That's that very last one, right there. OK. So we can think about this visually, which is really helpful for this proof. Now comes the fun part. So that was all our necessary tools for this proof. Now comes the fun part. So we take a polyhedron, and we put it inside of a sphere. And then in the middle of our polyhedron, we turn on a light. And then that gets projected onto the sphere. And we have a whole bunch of spherical polygons now on the sphere. And we can find the area of each of these, right? So at each vertex, we have 2 pi. All the way around the vertex is 2 pi. All the way around the vertex is 2 pi. And we're doing that because we're adding up the angles, right? We're adding up all of the angles in our polygons. So that means the vertices contribute 2 pi times the number of vertices that we have to the sum of our area. And then at each edge, there'll be a negative pi on each side. So that means the vertices contribute 2 pi v. Each face contributes 2 pi. That's the 2 pi right in the middle. And each edge, there'll be a negative pi on each side. So each edge contributes negative 2 pi. So then we have 4 pi, the area of the whole surface, is 2 pi v plus 2 pi f minus 2 pi e. Yay! Right? So now we just divide both sides by 2 pi, and we get the desired result. V plus f minus e is 2. I really like that proof. Just because I like spherical geometry. It was the first time that I was really challenged to think deeply about mathematics. That, wait a minute, Euclid's fifth doesn't work? Like, what? That was the first time in my life that I was really taken aback by mathematics. I really started to fall in love with mathematics. And that's why I really like that proof, because it uses spherical geometry. OK. So I have 2 more proofs. I think for the moment, I'm going to skip the next one. And I don't know how many slides I'm going to be skipping here. Actually, let me retract that last statement. This part's really fun. So the cool thing about this last proof is that it shows that this works not only for any regular polyhedra, but it works for any polyhedron that's homeomorphic to a sphere, which is a really big word that means if I could blow this thing up like a balloon, then it looks like a sphere. Okay, so mathematically, we say there's a bijection between the surface that I'm dealing with and the surface of a sphere. So what that means is just take a sphere, any sphere you want, and draw some spherical lines on it. So, or even parts of spherical lines. So maybe I'll just do that. So my claim is that formula this will satisfy that formula. So let's count the number of faces. Well, there's 1, 2, 3. Is that OK? Did I miss any? No, there's 3. Vertices. 1, 2. Edges. Well, there's 1, 2, 3. All right, so we have to do v plus f minus e. So that's 2 plus 3 minus 3. Yay. So you can try that as much as you want. It will always be true for anything that is homeomorphic to a sphere. Perhaps even more interestingly, it only works for surfaces that are homeomorphic to a sphere. So I actually have some solids up here that the Euler number is 2 for this thing, which I believe to be an icosahedodecahedron, though I may be mistaken about that. And then I have the Platonic solids up here. If you want to take a look at them, you can count them. If you want an exercise in counting, then by all means. And I even have a dodecahedron. And then I have some other surfaces that actually fail to meet this condition, that v plus f minus e is 2. So I have a projective plane and a Klein bottle. They were really, really hard to make because I had to access the fourth spatial dimension. Things got really weird. So I actually decided to escape 4D, and I just used scissors and tape instead. And then I have a torus, and this actually doesn't work for, it doesn't satisfy Euler's formula, because if I tried to blow it up like a balloon, I would have a donut, right? And that doesn't become a sphere. So it actually only works for surfaces that are homeomorphic to a sphere. Yeah, so it's a topological invariant. It determines the type of surface that we're working with. And I actually have some of the numbers up here. So for an n-hold torus, the number's not 2. It's -2 times n minus 1. It's 0 for a Mobius strip. It's 1 for a projective plane. So here's my projective plane, and it's 1 for that. Do you guys know what a projective plane is? No. All right. It's not critical to the story at all, but I can show you what it is real quick. You know what a Mobius strip is?
Yes.
Okay. So a Mobius strip is like if you had a strip of paper and you made one twisted and connected it, that's a Mobius strip. So a projective plane is you have to do that twice. So you have a piece of paper, and you have to connect the edges in such a way that the arrows on the opposite sides match up. So if I took this and twisted it and matched the arrow there, took this, and then at this point I have to go into 4D. It's really hard. And then you get a real, it looks like this. It looks like that. I mean, this is what a computer tells us it looks like. Okay, this is the proof I'm going to skip for a moment, because I think I have a better one. But the other one I'm going to use does use graph theory. So graph theory is another fun area of mathematics, and Euler is responsible for it. He sort of stumbled upon it trying to solve a puzzle. The bridges of, I forgot, Koningsberg or Koningsberg. I don't know how to pronounce it, but so he's trying to solve this problem, and to solve this problem, he sort of invents this whole new branch of mathematics called graph theory. And you can actually prove Euler's formula for polyhedra using graph theory, which seems extra special cool because Euler's responsible for the formula and responsible for graph theory. So it's like double Euler. So we'll define a graph. A graph is a collection of vertices and edges. Not a graph in the algebraic sense, a graph in the sense where we sort of we have vertices, and then we have some edges that go between them. So here's an example of a graph in graph theory. All right, I'm going to skip this part, so bear with me for a second. OK, so this one is perhaps better. Here's another proof due to Cauchy. Did I pronounce that right? All right, good. His idea was a bit different, similar, but it uses graph theory too. And it also uses induction, but I think this one's a bit easier to explain by drawing pictures. So he starts by taking a polyhedron and then drawing its corresponding graph. So you can see for a tetrahedron, there's 4 vertices, and each of those 4 vertices are represented here. And then if there is an edge that connects the vertices, then he draws an edge on the graph to connect those vertices. So here's the corresponding graph to the tetrahedron. Now what we have to imagine is that the number of faces here is 4. So we have to count 1, 2, 3, and then everything else is a face. Is that OK? All right. it's easy to show that it works for this. Just count them up. How many vertices are there? There's 1, 2, 3, 4. How many faces are there? There's 1, which is the outside. 2, 3, 4. 4 plus 4 is 8. Let's subtract the number of edges. 1, 2, 3, 4, 5, 6, 8 minus 6, 2. So it works in this case. Now what we'll do is we'll take any other polyhedron and reduce it to that. So here is the graph of a dodecahedron. This is the graph of this. So we have each vertex corresponds to each of these vertices. In fact, each face of a dodecahedron is a hexagon. And you can see that each of these is 1, 2, 3, 4, 5. Okay? So here's the graph of a dodecahedron. We're going to reduce this graph to that one. So start with a general graph of a polyhedron. And if there are faces that are not triangles, we add in edges so that there are triangles. Here's the graph where I added in the edges, so now there's triangles. That does not change the value. So inherent in this picture is a value v plus f minus e. I don't care what it is. It doesn't matter what it is. But if I took the number of faces plus the number of vertices and subtract the number of edges, it's going to be some number. Yeah? And the claim is that if I make triangles out of all the faces, that won't change that number. Because if I add an edge, then what happens to the number of faces? If I add one edge, the number of faces increases by 1. And we're adding f and subtracting e. So I'm adding 1 and subtracting 1. It doesn't change that value at all. So whatever v plus f minus e is for this picture, so v plus f minus e is the same for this picture. I've added a bunch of edges. At the same time, I've added the same number of faces. And since I'm adding the number of faces and subtracting the number of edges, that number, whatever it is, doesn't change. Now, we take this picture, and whenever there's a triangle along the outside, we remove the edges until just one triangle remains, or until this one. You can choose this to be your base case, and then until this remains. So here's an edge. I take it away. So that subtracts 1 from e, and subtracts 1 from f. So two cases occur. We either remove one edge and one face, and so v plus f minus e is unchanged. Or we remove two edges and one vertex. So if I have, for instance, after I've, let me find one. Well, there might be a case where you have let's just say, for the sake of argument, you have something like that, where you have to remove. That's not right. There might be a case where you have to remove two edges, in which case you'll remove a vertex, I promise. I'll have to think about that for a second, so forgive me. Regardless, v plus f minus e is unchanged. Let's trust Koshi. He was smarter than me. Eventually, we get to a graph that's just one triangle, if you want to reduce it that far, or we can just reduce it to this one. In either case, you get v plus f minus e to be 2. So you might think, okay, well, what's the importance of this theorem? Why do we care? It's actually led to some pretty interesting things, including a proof of the FourColor Theorem, and that was in 1978, if I can remember dates. And so I had the famous or the infamous. So the FourColor Theorem is perhaps an infamous proof Why is that? Because it was the first proof done with a computer. And also advances in topology and surface classification and knot theory. I am absolutely no expert in topology, but if any of you are and know how to expound about how v plus f minus e is important in topology, then by all means, I'd like to pick your brain, I guess. So for more information, you can read Euler's Gem, written by David Richardson, who was a professor at U of M. And there are pages on the internet that have lots of proofs of Euler's formula. And if you are interested in making your own polyhedra, then you can get cutouts and make your own. Or you could just take a course in graph theory or topology, which is one that I recommend. Perhaps I'll see you there. That's all I have for you. Thank you.
Thank you, Dan. If you have any questions for Dan, I'm sure if you have